Hello everyone, myself M. Raja. I am from third year CSC department. Today my topic is about equivalency of type expressions in automata theory and compiler design. Let us go to our topic equivalency of type expressions in automata theory and compiler design. Introduction to type expressions. Equivalency. This presentation explores the concept of equivalency of a type expressions within automata theory and compiler design. Understanding type expressions equivalency is crucial for the optimizing type checking and code generation. We will examine theoretically foundations and practical implications in compiler constructions. Let us go to the another slide. Basic concepts of type expressions. Type expressions specify the structure and behavior of data types in a programming languages. They can simple, example integer, boolean or complex functions type and recursive types. Formal definitions help in the analyzing and comparing type expressions systematically. Automata theory and types. Automata theory provides formal models for recognizing and processing type and type relations. Finite automata can model regular expressions such as strings of data and patterns. These models underpin many algorithms used for type checking and interfaces. Role of type equivalence and compiler design. Type equivalences determines whether two type expressions can be considered the same during compilation. Accurate equivalency checking ensures correctness in type casting function calls and data manipulations. It also impacts optimizations and code reuse in compiler implementations. Types of type equivalences. Structural equivalencies compare the shape and component of type independently of their names. Name equivalencies relies on expels and naming and declaration to determine type sameness. Understanding both types helps in designing flexible and robust and type systems. And structural type equivalencies. Structural equivalencies consider two types equivalent if their structures are identical. This approach simplifies the type compressions and especially for the complex or recursive types. It is a common language that favor type flexibilities like ML or Haskell. Name or nominal type equivalency. Name equivalency requires that type have the same identifier or declaration to be considered equivalencies. This approach emphasizes explicit type declaration is used to languages like Java and C++ or C. It helps to prevent accidental type mismatches based on structural similarities only. And automata models for type equivalencies. Finite automata can be modeled regular type expressions to test and equivalency efficiently. Equivalency checks involves constructing automata for each type expressions and comparing their behaviors. This method provides a formal and automata approaches to types analysis. Regular types and automata. Regular types are those can be declared by a regular expressions but and recognized by finite automata. Many data types such as strings and lists are modeled as a regular types in automata theory. Automata based on techniques enable efficient types interference checks for the regular types. And recursive and complex types. Recursive types define types in terms of themselves which completes equivalency checks. Automata models can be extended to handle recursive types, vivoc cycle and fixed points. Proper handling of recursive types is essential for languages supporting complex and data structures. And algorithm for type equivalency checks. Algorithm typically involve automata constructions, minimization, and compression. These algorithms can be optimized for specific type systems to improve performance. Correct implementation ensures reliable type checking in compiler workflows and practical applications in compilers. Ensure type equivalences is a vital for the correct type casting. Overloading and polymorphism and automata based on methods support compiler features such as type interference and generic programming. These techniques contribute to safe and more efficient compiler code. And challenges and limitations. Handling complex recursive or polymorphism types can be computationally intensive. Difference in type system across languages may require tailored and automata models. Ongoing research aims to improve the scalability and precision of equivalency algorithms. And summary of key points. Type expressions equivalency is fundamental for correctness and optimization in compiler. Automata theory offers formal looks, tools to model, analyze, and compare types. Both structural and normal approaches have their roles. Dependency on language design and conclusion. For future directions, advanced in automata based on techniques continue to improve the type analysis in modern compilers. Integration of automata models with type interference algorithm enhance languages or rebootness. Future researchers may focus on handling even more complex type systems and their automata representations. And finally, thank you.